let me know. Okay, now we talk about the exponential function the other night. Okay, exponential function is just start with the fixed number as a base and the variable x is up there. But the most interesting one that we are going to be interested in future is this function. Okay, it's called natural exponential function. And the base is a special. Okay, the base is e. You know, a is like a pi, 3.718. And this is going to be e. And there are different ways to introduce the e, but you don't need it for the time being. We're just working with the function. All other properties of the function is the same for the e. The domain is all real numbers, for example. It's a positive, increasing, everything we talk about it. So you should be able to work with the e. There are a couple of phenomena, mathematical modeling involving this function. So we'd like you to be able to work and especially using your calculator. So you may be given these type of problems, okay, that you end up with working with this function, okay. So for example, and if you want to calculate, this is going to be part of the deal. So we may give you this, or we are going to give you this type of example for the exponential function. So we are going to be giving you, this is those model that we are going to talk about later. Suppose f of t is equal to the 500. Okay, 500 e to the 0.03 t. Okay, this is the model that in future we are going to call it growth model. It's like you can put your money in the bank, start with the 500, and the bank give you 3% interest. So you want to know how much money are you going to have after t years, t months. So that's a model. Just growth like the coronavirus, for example. Okay, initially this is going to be the one. The rate of interest, the growth is 3%. You want to know what would happen for the next 6 months. So this is the way we're going to do it. This 500 would be called initial value. This initial value means just at the beginning, when t is equal to 0. Then for the time being, we give you the model and we ask you to operate with it. Okay, so this would be given to, and then we ask you to, okay, this is going to be the one. We ask you to evaluate it. And eventually you are going to evaluate it at some point for us. Okay, evaluate f. Okay, f at a couple of numbers. Okay, we may ask you to evaluate it at t equal to 0. And okay, t equal to the 50. Okay, so this is going to be various cases that we have. You just substitute and get your result. So the solution is, get to know your calculator, the way you're going to operate. F of 0 is easy. So it's going to be f of 0, and this is going to be 500 e to the 0.03 times 0. Okay, so this is going to be 500 e to the 0. E to the 0 is 1. So 500 times 1, which is 500. So this is going to be the initial value, whatever it is, money, numbers, objects. So that's f of 0. Okay, any question? F of 50, just substitute. F of 50 is going to be e to the, okay, it's going to be e to the 0.03 times 50. You have to use your calculator, okay? So, you can multiply the top if you like. This is, oh, I missed the 500, sorry. It's a times 500. So f of 50 is going to be equal to the 500 times e to the, that would be 15, 1.5. You cannot leave it as e to the 1.5. So on the test, you have to use your calculator and to give us this number. Okay, make sure that you know how to identify your calculator, these numbers. So this is going to be ln, that we're going to use it later on. and you go to the second and you click the ln, so that give you the e. Okay, e, and then you put the numbers in. So the number is 1.5, so e to the 1.5, so that give you the result. Okay, then you multiply by 500, multiply by 500, and this would be your result. Okay, so make sure your calculator give us these numbers. Okay, some calculators would be a little bit different, but not too different, if you like. So it's going to be 0.8, but if we are going to talk about the money, okay, or the units, so I'm going to run this one. If they give you the instruction, you run that, or otherwise you can leave it. So in this case, it's going to be, okay, so this would be the final answer if you want to run that. Okay, otherwise you just write it down as is. Okay, so this would be the final answer. So make sure your calculator are ready. So we give you a couple of numbers and we ask you to investigate it. We may give you a negative number or positive number, and as we go on, we give you more examples. Okay, any question? This problem would have 3 parts at the end of tonight, or maybe next time.
Yeah, where did you get the 1.5?
I just multiply this one first.
Okay.
When you use calculator, you do all of them together, but I did it first. Okay, so this is going to be one application of the exponential function. In your book, they use it for the interest rate. So we're going to discuss that one. You have a number of them in your assignment, and we usually give you 2 questions on this one. Okay, so what is going to be interest rate problems? So we call it compound. That's it. Compound interest problem. It would be resulted in 2 formulas that you have to know them. Okay, now you know that you put the money in the bank, okay, or you borrow money. So the way they are going to calculate the interest, there are different ways to do it. They may calculate the interest at the end of each month, okay, or they may do it at the end of each year, or they may do it every 4 months. So it depends how many times they are going to compound it, if you like. So we want to find a formula that gives us these how many times. Or sometimes you are not going to leave the money in the bank. Okay, you invest in in the stock market, and you want to know what's going to be your money at any time. So in that case, the machine should be ready to compound it for you anytime you want it. So you are going to have 2 different formulas. So I just explained how this formula would be related to the exponential function. Okay, then at the end, you memorize those 2 formulas. So suppose you start with the money in the bank. Okay, so if you start with P dollars, if you like, okay, that's your starting target. So if you start with the P dollars, if P dollars are going to be deposited in the bank, okay, in an account, and this is it, in an account that gives the interest, okay, earning or giving interest, okay, interest at the rate, at an annual, okay, rate of R%, R, okay, R, and if they just compound it, they are going to calculate your interest compounded at okay, at the end of each year. Just they do it once, okay, at the end of each year, at the end of the year, if you like. So if this is going to be the case, then we would like to find a formula for it. The formula would be if you suppose amount of the money AT is going to be the money in the bank after T years is the amount. Okay, it's going to be the amount of money. Okay, your money after T years. Okay, so A1 would be after 1 year. Okay, then you just keep going. If this is going to be the case, so what's going to be the formula in question? You see, after a year, at the end of the first year, if you go to the bank, this is how the bank would calculate your money. It would be your starting point, money that you invested, plus the interest. Interest would be R% of your money. So it's going to be R, the rate, times P. Okay, you can factor out the P, so that give 1 plus R times P. Okay, this is going to be your money at the end of the first year. You may call it P1. You leave the money, and then you come back next year. So at the second year, the bank would give you your money in the previous year, and they give you interest on that one, RP. Okay, RP1. Then this would be 1 plus R times P1. Okay, but the P1, your previous money is 1 plus RP. So this is going to be, you already got the 1 plus R. Then you multiply by the money previously you did have, is a 1 plus R times P. So this would be, so at the second year, so your money would be 1 plus R squared. Okay, 1 plus R squared times P. So that would be your money at the second year. You can repeat this one over and over and over. So if you repeat it after T years, your money in the bank is going to be 1 plus R to the T. Okay, 1 plus R to the T times P, or just P times 1 plus R to the T. Okay, so this is going to be money in the bank if they just compounded once a year. Okay, once a year. But if they are going to, if they compounded each month, so they have to do it 12 times. Okay, so your formula would be different. So what we are going to do is, suppose they are going to compound it n times, if you like. This is, if you do this R is the percent of your interest for a year. If you want to do it 12 months, so you have to divide the R by 12. Okay, it's like when you do your credit card. So the formula should be modified. So if they compounded n times, if it is compounded, okay, n times each year. Each year you have to modify your formula. Okay, you modify the rate is going to be R over n, and the time, the number of the time for 1 year is T. So for 1 times, so it's going to be n times T. So the formula would be, so if component n times during the year, so again, to get this famous formula that you make a note and for the next test or quiz. So the money in the bank in this case is going to be the P, the money that you start with, is going to be 1 plus. You have to divide the rate by the number of the times that you compound it. Okay, and this is going to be n times T. Okay, n times T, this is going to be the money in the bank after T years if you compound it n times. Okay, so they call it simplest interest, simple interest. They call this one simple interest. Okay, interest compound, some simple, simple compound interest, or just simple, I'm sorry, I should give you the compound. Simple compound interest formula. So if you give it the number of the time that you're going to compound it, you have to use this formula. Okay? But if you are not going to be patient and you would like to count your money at any minutes, any second, so then the number of the times that you're going to compound it would be quite a lot. Quite a lot means this n getting closer and closer to infinity. If you get closer and closer to infinity, I talked about the other night. So this formula would be closer and closer to the e, if you like. So if you just doing it all the time, so if n goes to infinity, okay, this means continuously you're counting your money. If n goes to infinity, and okay, this is going to be the one, and the account, okay, and the account compounded all the time. Okay, this is it. It's going to be compounded all the time or just continuously. We call it continuously. Continuously, so the result is going to be then this expression over there would be getting closer and closer to there. This is going to be a of t equal to, you get the p as is, but this expression goes to the e to the rt. Okay, and this is why this formula is going to be important. That's a growth formula. In calculus, we prove it nicely, but over here, we just accept it right away. Okay, so this formula would be, okay, for the interest rate, continuous, we call it continuous. Okay, continuous compound interest formula. Interest formula. They are going to tell you in the problem, when they say compound continuously, you know that you have to use this formula. Okay, P is the money that you put in the bank at the beginning, R is the rate, T is the time. So in this model, we give you two questions. A time T would be given, they ask for the money, you substitute using your calculator. The other way around is the money would be given and we ask you for the time. We have to wait for that one, but we just put them together. And this is the way we do it in calculus. In calculus, there is a third part that you cannot, you cannot do it now. So you must know these two formulas, okay? And now we can give you two examples, okay, to get these numbers. And just because you have a group of them in your book and it's going to be part of your assignment. Okay, so if you want to do it, you better do it as, just similar to this one, just to make sure to remember it. Not a big deal, but I don't want you to miss it. Okay, so example. Any question? If they say continuously, use this formula. If they say compound twice, 3 times, 4 times, use this formula. Okay, so this is it. I'll give you two problems so that you know that how we're going to do it. So we go with the first one. An initial investment. Okay, initial investment of $2,000. You put the 2,000 in the bank, earns how much? 8%. 8% interest compounded continuously. As soon as I say continuously, you have to use this formula, PRT, okay? Continuously. So they put the money in the bank. The formula is going to be continuous compound. So they ask what, okay, they ask what will the investment be? Okay, investment be worth in 15 years. In 15 years. That's it. So you focus on this one continuously. Okay, since it's continuously, you are going to use this formula, A of t equal to the P e to the RT. Bring your numbers. Your R is 8%. Okay, 8%, this is going to be 0.08. Okay, and your P is 2000. Substitute to get your model. We call it growth model. It's going to be A of t is equal to 2000 e to the 0.08 t. And you wait for those two questions. We cannot do the second part. We need a log function that we're going to discuss tonight. Okay, so t is equal to 15 years. Okay, so A of 15 is going to be equal to the 2000 e to the negative 0.08 times okay, times 15. This is where you have to use your calculator to get this number. Okay, if you like 15 times 8 would be 120, so it's a 2000 e to the, okay, it's going to be e to the, it's going to be 1.2, 5.2. Okay, then you can use your calculator that we talk about it. Okay, so second on the ln you get exponential function. Okay, exponential, you need 1.2, 1.2, then multiply by 2000, multiply by 2000, 1, 2, 3. That's it. That give you the money. 6,600. Okay, so that's going to be 6,640. Okay, it's 40.23. It's money, so we go with the 2 decimals. So the money in the bank after, okay, after 15 years would be $6,640.23. Okay, and you're done. So don't miss it. It's easy problem. Okay, compound continuously in this case to get these numbers. Okay, any question? So that is case 1, compound continuously. I'm going to give another one when it's compound several times. Okay, when it's composed just finite number of the times, then it's not going to be continuously. Then you have to use the other formulas. Okay, are you done? So have another one. Investment is very similar, but they give you the number of the times that they are going to compound it. So example, what is this one? Initial deposit of and initial, okay, you deposit initial deposit of $1,000. Okay, $1,000 earns 9%. Okay, 9% interest. 9% interest compound. Okay, compounded monthly. So monthly means twice in a year. Sorry, 12 in a year. Monthly, okay, because this is the finite number of the time, so it's not going to be continuously, and you have to use the other formula, okay? So what is the question? The question is how much money? How much? Okay, how much will be in the account? Okay, how much will be in the account in 4.5 years? So that's going to be the problem, okay? So you are going to focus on this one. Compound monthly means in a year, you are going to do it twice, 12 times. So it's a finite number of times, so it's not continuously. So you have to use the other formulas, okay? So the solution is going to be, you identify that your money starting point is $1,000. Your interest is 9%. Okay, 9%, which is going to be 0.09. And you have a number of the time that you compounded is equal to 12. Okay, so it's a finite number. So you have to use this formula. A of t is equal to the p times 1 plus r over n to the n times t. Okay, make sure you use the correct formula. So substitute to get your model, then whatever number it's given to you can operate. Okay, so the model for this problem is going to be 1000, 1 plus the rate of 0.09, number of the compound 12. Okay, and this is it. And it's raised to n times t. Okay, your n is 12, 12t. So that would be the model. And the t is in years. Okay, t is in years in the formula. Okay, this is going to be your calculator, your model. Then what you have is you wanted to find out after 4.5 years. Okay, so t is equal to the 4.5. So write down 4.5. And then you are going to find a of 4.5. Okay, you substitute. That give you 1000. Okay, this is it. 1000 times 1 plus 0.09 over 12. And this is going to be 12 times 4.5. 4.5 to get this number. Again, you have to use your calculator, simplify it as much as you can to get these numbers. Okay, different way to simplify it. You may start with this one, add it to the one, simplify everything nicely, and then eventually find the final answer. So it's going to be a 4.5. Okay, depends how you operate with your calculator to get these numbers. Okay, just do it step by step so that you can see it. I do the 0.09. I divide it by 12. So that give me, just write it down whatever I do. So it's going to be 1 plus, this is going to be 0.0075. Okay, then I multiply the top. It's the way I do it. It's going to be 4.5. So the top would be 54. Okay, so basically I have to go multiply this 1000, and that gives me 1.0075. Okay, raise it to the 54. Okay, to get these numbers. Okay, and then basically, if you use a calculator, you can check. So the final number is going to be, that's it, 1497.004. Okay, so that give you the number in, okay, the number in questions. Okay, so this is going to be the case. Okay, it's a 1.000075. Okay, and then I have 54. So that's, just check it to get this number. Okay, so they are not difficult. Just don't miss it for your next quiz. You get your assignment in this section. Most of them are covering by this type of ideas. Okay, so the modeling and then getting these, getting these numbers to be able to do it. Okay, so we will come back to it because we finish this problem when we get more information from the log functions. Okay, so that was what we need so far for the exponential function. Okay, so get the graph of this exponential function, just the application for the time being, to be able to do it. This type of model got quite, interesting various application in future, but for the time being, we're just getting to know it. Okay, any question? Now, that was exponential function. Quickly, we want to get the opposite or the inverse of this function. Remember, we talked about the inverse function. Inverse function was what? You get the y equal to the f of x. If you can solve for x, the result is going to be the inverse function. So we are going to introduce the inverse of the exponential function. The inverse of the exponential function is going to be the log function. Okay, so that will take us to the section 5.2. Okay, to get to the logarithmic function. So this is 5.2. Okay, this is going to be logarithmic. Okay, that's it. Logarithmic function. This is not going to be good, so I have to change it into new. Okay, so I use this color. Okay, this is it, logarithmic functions. We are going to work with this function. So how we're going to define this new function, the log function. Okay, so there you are. Remember, for the exponential function, we did have the base, so we're using the same base. So this is it. Suppose b is a positive number. B is a positive number. Okay, it's going to be a positive number as usual with b not equal to 1. Okay, that's the one. Now we are going to introduce the log function. So the logarithm, okay, or the log function. Okay, function with or at with base b. Base b is going to be denoted by, that's it, log of x with base b, and is defined to be inverse of the exponential function, and is the only reason that you got the inverse function is this one, and is defined by, this is it, y equal to log of x at base b if and only if. You see the inverse function? You must solve for x. If you want to solve for x, we define it by x equal to the base b to the y. Okay, so they are inverse of each other. And we already talked about the exponential function, so we can use those property to introduce the log function. So y equal to this is just like a machine going from one side to the other side and just coming back. So this would be log function. Okay, so before going on, there are a couple of different cases that we can introduce. Okay, so we know everything about the other side. Okay, we know everything about the other side because that's exponential function. We know that the domain is all real numbers. We know that the range are positive numbers only. Okay, so we're going to use this fact. But before going on, so getting a various definition or the special cases. The special cases are going to be if b is equal to 10, okay, the base 10. If this is going to be the case, then log of x with base 10 is called common log or the decimal logs. Okay, this is going to be called common or the common. Okay, common log functions, logarithm. Okay, function. We have a special notation for it. You know, in your book, they give you the 10. But if you're going to be in calculus, we drop the 10. Okay, so it is denoted by, it is going to be denoted by, okay, we denoted by, this is it, denoted by log x only. Okay, so if you see log x, we mean log x at base 10. Okay, I won't write the 10. Okay, so that's a very classic, classic format of this function. Okay, so therefore, if you want to get information, y equal to the log x at 10, if and only if exponential function would be x equal to the 10 to the y. Okay, so it's going to be, see, that's going to be, I'm going to drop it. So if you see it, you must know it yourself. That the log, you see, there is no 1 for the base. So you cannot say that, the base is 1. No, the base is 10. The base is 10, but we don't write it down. Okay, so this is one case. Any question? So, when you sit, if you sit on the test, then you realize that the base is 10. Now, the other famous one is if b is equal to e. Okay, if it's going to be the case, then that's the most popular one. Then log of x with the base e is called the natural log. Okay, this is going to be called, okay, it's going to be called the natural log function. Natural logarithm. Okay, that's one. Make function. We have a special notation for this one. Okay, it's denoted by ln of x, natural log. ln of x. So we call it ln function. So if you write ln x, we mean log x at base or with base e. In calculus, we use ln x only all the time. In physics, chemistry, all of them. You'll see in a minute why we're just using the ln x. So all the charts, tables, formulas, they're all expressed in terms of the ln x rather than the other one. Okay, so our definition now is going to be, therefore, if you say y equal to the ln x, if you want to switch it, so you switch it to the x to the base e to the y. So e to the y is a natural exponential function. Ln of x is a natural log function. Okay, so that's the definition of the log function. There are different ways to define it, of course. There is another way to define it in calculus. We do the same thing if you take calculus for business. But if you go with the calculus 1, 2, 3, in calculus 2, they can introduce this log function too. But we are just staying with this type of notations. Okay, so we can go from one side to the other side to get this famous function. So we are going to check some property of this function. Anything you want to say, you have to go to the other side. You see? Of course, we want to talk about the domain of this function. Domain means what type of x can you have, or what type of numbers can x, can x receive. So x is coming here, coming from here. So you see this is in the range of a to the y, or this is e, 2.7, so it's positive. So this means this x never negative. So the domain of the ln function is positive numbers only. In particular, it's never zero, because this x cannot be zero, because e is 2.7. So ln of zero is not defined. And it must be positive. If it's going to be negative, not in this course, you see, ln of a negative number does exist, but they are complex numbers. And one reason that we created complex numbers were to take care of these ln of a negative numbers, because they use in physics quite a lot. So they did have something that it's happened in the nature. So they just want to find a mathematical model for it. So that's ln of negative number. But in this course, make sure that you know that we cannot define ln of a negative number, or we cannot define ln of 0. So I'm going to put some properties of the ln together from this exponential one, just preliminary results of the ln function, okay, for the application in future. Okay, any question? So make sure you know the names, okay, the difference between these ideas that we talk about it and the notion of the natural log. Again, on your calculator, you have to identify it because you have to do it for us. This is ln. Okay, you got the log and the ln, but mostly we use ln. So if you put the second, ln would be changed into the exponential function, or otherwise it's ln. So for example, if you want to find, okay, so that's the second, and I click on the ln. That is, oh, I'm sorry, not the second. I missed that. Okay, if you click on ln, that's going to be ln. Okay, so for example, if you want to find ln of 2, that should give you 0.69. So it's equal to 0.69. Okay, so get to know it, because you are going to do it for us, in the application problems that we're going to have. Okay, so that is the kind of evaluation of the ln. Now let's get those properties from the function point of view, which is very important for us. Okay, so this is it. So what is going to be the domain, or just some prop? The domain is important, so I talk about the domain first of the ln function. Okay, so because you have a couple of problems just with the domain. So what's going to be the domain? Okay, the domain of this function in general, y equal to the log of x with the base b. Okay, that is going to be the case. So if we just remind you the definition, Okay, remind you that, recall that y is equal to the log of x at base b if and only if, okay, if and only if x would be b to the y. It's the inverse function. So this means x coming from here. X must be positive. Okay, so this means so the domain of this function is only positive numbers. Okay, and the range of this function, the range, you see the range is y values are going to be in the range, okay, and the x values going to be in the domain. So y, where is the y is coming from? Y is coming from the exponential function, and you know that exponential function is defined forever. So that's why the range of this function is r. So this means any real number, if you think about any real number, that number is ln of something. But this part is the most important part, the domain. Positive numbers only. It cannot be negative or it cannot be zero. We give you one question on this one. Okay, so it doesn't matter which type of the log you are going to use, the domain would be the same. So this is the type of question that you get because we need it for calculus. We wanted to find the domain, okay, the domain of each function. Okay, domain of each function. So we go with the first one. The first one, the function is f of x equal to, let's say, log of, let's say, x minus 1 at base with a base 5. The base, the type of the log, they are not important. The inside, the input. The input cannot be negative. Must be strictly bigger than 0. So this is going to be the solution. Okay, so I rewrite it again. So this function is going to be defined if the inside is strictly positive. Greater than 0, not greater than equal to. If you say equal to means you believe in log 0, which is impossible. Okay, then you solve this inequality, that's it. So that will give you what? X greater than 1. So the domain, you have to write down interval notation. You start with the 1 and you go on forever. That is going to be the domain of the function. Any question? Because if you pick any number less than 1, inside would be a negative number. So you cannot have a negative number. That is the type 1. Any question? Type 2 is this famous function for calculus, y equal to ln of, okay, y equal to the ln of x squared minus 4. See, that's the ln function. It doesn't matter, it's a log function. So the inside cannot be negative. So this function is defined if x squared minus 1 again is positive. Solution. Okay, so that's it. I have the ln of x squared minus 4, and you have to guarantee that this is positive. You see, you have to solve this inequality. We talk about it, you can factor it and use a chart, or you can use move the 4 to the other side, take the square root. Remember, we did it before. So one option is going to be, you can write down as x squared greater than 4, or you can use the square root method, okay, to get this one. So what is that? It's going to be radical x squared greater than radical 4. What is radical x squared? Any suggestion?
Absolute value of x.
Excellent. Absolute value of x. Absolute value of x greater than 2. Okay, remember absolute value of x greater than 2. This is 0. 2 to the right, negative 2 to the left, greater than. When it's greater than, you go to the right. So you are going to be here, either here, and symmetrically, you may be here. So this is a negative infinity, and this is a positive infinity. Okay, so what's going to be your domain? Domain is start from negative infinity, stop at the negative 2, union with, start at the 2, and you go on forever. So that give you the domain of the domain of the function. Okay, any question? So don't miss it. It's like the radical function that we check, but in the radical function we write usually greater than equal to the 0, but there is no equality sign to get this number. Okay, so x squared minus 4, it's a very popular function, so from time to time you may have to take care of this one. Okay, that's a case 2. Any question? So be careful, sometimes they switch this number. If they switch it, this direction would be less than. You know that it's going to be less than, you are going to be in between. We're going to be between negative 2 and 2, but this is greater than. And you will see it, when we get to those practice tests or the quiz, you see all the possibilities. Okay, that's case 2. Any question? Now, this next one, again, it's used in the application problem, so just want to make sure you know it. There are a group of functions when you work with the ln function of this format. F of x is equal to, is going to be ln of, you give it a quadratic form, something like x squared, okay, plus 3x, okay, plus 3x, and the 5 here. You see, this is the one. Okay, again, you know that this function is defined if the inside is positive. And the inside is a quadratic expressions. Okay, remember, we did have something we call it polynomial inequality. We checked that one before. So, and this is it. Solution would be, again, we said that f is defined. F is defined when x squared plus 3x plus 5 is positive. But officially, if you want to solve this inequality, remember you have to let it equal to 0, find the so-called critical numbers, get the chart to find out when this is going to be positive. But let's see if we can do it. You see, if you put x squared plus 3x plus 5 equal to 0, okay, so you cannot factor it. You cannot factor it because you need two numbers with the product of 5 and a sum of 3, impossible. Even if you try to use, quadratic formula, you can't do it. I mean, the delta would be negative if you want to go with the quadratic formula. Okay, you see A is 1, B is 3, and the C is 5. So the discriminant would be a negative if you like. I can show you, but you don't need it. So you see A is equal to 1. It's not factorable that you'll be able to factor it. B is equal to 3, and the C is equal to 5. Remember, delta, or just discriminant, is a b squared minus 4ac. See, if you substitute, your b is 3. So 3 squared would be 9. Minus 4ac, 4, 1 times 5. So that gives 9 minus 20, which is a negative 11. See? You can't solve it. And we talk about it. If you cannot solve it, the sign is the sign of the x squared. If you put any number, you see, any number, you can put 0, x equal to 0. If you put x equal to 0, that gives you 5 all the time. So this means this is going to be true. You see, if you want to remember, when we have two solutions, we get a chart to take care of it. You see, this is going to be your chart. You have the x from negative infinity to positive infinity, and you have a so-called f of x here. You see, it's you didn't get any solutions. So when there is no solution, the sign is the sign of the x squared, which is positive. Or just replace x by 0, that gives you 5, it's positive. So this means the domain of this function is all real numbers. It's very popular function for future if you want to take any other courses. Okay, and you will see it from time to time, so you should be able to, you know, they ask you for the domain. Whatever you want to do with this function, you need the domain first. Okay, so these are various possibilities that you're going to have. So just make sure that you're able to take care of this part. The one in your book, there is no x squared. Okay, it's a 3x minus 1, 2x plus 4, but this is it. You need this type of function in future, so why not? We get to know them now, and then we use it in future to get the domain of these famous function. Okay, any question? So that was the domain of the function. I just want to tell you that what you have in your book, you see, the domain that you have, they are simply, yeah, that is ln x 3 minus x. I just do one of them for you, but you know, this is nice to know because this is the way you are going to use it in future. So you see, from your book, if you like this, you have a couple of them. This is, yeah, you have a couple of versions. I'm just looking for something. No, they are all easy. You see, this example is from your book. Is number 68. Number 68 on okay, on 5.2. It's just a little bit not bad. Some people they miss it. You see, that's it. F of x equal to the ln of 3 minus x. You want to find the domain of this function. Again, the inside must be positive. Okay, so this is it. The inside must be positive. Solution. So you let 3 minus x to be f is defined, if you like. F is defined when or if 3 minus x to be greater than 0, not equal to, remember. Greater than 0. Okay, so you just move the 3 to the other side. Then just make sure that when you divide by a negative 1, just switch the sign. So x would be less than equal to 3. Okay, we divide by a negative number, so we have to switch it. So the domain is going to be what? It's going to be 3 less. So it's a negative infinity up to the 3. There is no equality sign here, of course. So that gives you the domain of the ln function to get these numbers. Okay, any question? So I pinpoint, you know, the domain separately, so that you know that this is important and it's going to be used. Okay, so that give us a version of the function, ln function. We can talk about the graph of this function. Okay, so what is going to be the graph? The graph is very unique. As soon as we graph it, it's done. So you may not see it to be do anything about it. Question: is it x less than or no, just less than? It cannot be equal to. Okay, it's just less. Okay, remember, if it's going to be equal to, no equality. If it's going to be equal to, then the ln would be 0, and the ln of 0 does not exist. Okay, now to get to know that the graph of this function a little bit. Okay, so what is going to be the graph? The graph of, we stay with the ln x, which is the most popular one that we are interested in, ln x. Okay, so to get an idea of this graph, you can use your calculator if you like to get some points. But I'll give you some information to start with. We know that the domain of this function is all positive numbers. Okay, that's going to be the one. This is going to be the domain. Then if you want to find ln of, okay, ln of 1 if you like, we are going to see it in a minute, but you can use your calculator. Ln of 1 would be equal to 0. Okay, this is the 1. If you want to investigate the end behavior of these functions, if x goes to positive infinity, if the number is getting bigger and bigger, the ln would be again bigger and bigger. So this is going to be the case that y goes to positive infinity. Okay, that's the 1. Then you cannot have x goes to negative infinity because x cannot be negative, but x start with 0. So if x start with 0, okay, 0, and even the 0, you cannot have a negative number. We usually write 0 positive, means you can go to the 0 only to the right. And if this is going to be the case, the ln would be smaller and smaller, and that goes to negative infinity. These are the ones that you can test with your calculator, and they are going to be done in more details in calculus. Really, we're just borrowing, or we can give you just the graph and you just see it. Nothing else that can be done at this level. So if you want to graph it, this is it. Ln of 1 is 0, so this is going to be x equal to 1. Okay, is equal to 0. Now you can collect more points if you like using your calculator to get these numbers. But you see, x goes to infinity, positive infinity, that gives you infinity. F getting closer and closer to 0 is a negative. So this is going to be a kind of graph. If you look more, okay, this is going to be the graph of y equal to the ln of x. Okay, just knowing it that is going to be the case would be enough. Or you can put some numbers in the table, but use your calculator to get more points. If you remember, for the exponential function, you see, if it is 1, exponential function was this one. Remember when this is going to be the graph of y equal to the e to the x. So that's e to the x, and this is going to be, okay, ln of x. They are inverse of each other, you see. One of them is inverse of the other one. As you can see, it's somehow you can put them together. If you want to use this so-called symmetric property, it's going to be symmetric with respect to this line. You see, if you get the line, this is the line y equal to the x. So this graph is going to be symmetric with respect to this line. So this means if you get a point here, go to this line, equal distance, that give you the other one. You see, if you get a point here, go to this line, equal distance, that give you the other one. So we say that the graph of the e to the x and ln x are going to be symmetric with respect to this line, y equal to the x. Again, you see, you get more information in future. Okay, so that's the nature of the graph of the function. So if you want to do anything with the ln, you have to use your calculator to get these numbers. Okay, any question? I can give a short break. We come back. There are some properties, algebraic property of this function that enable us, to solve various problems. So we can talk about that one. This is 5.2. In 5.2, they just introduce the ln function, and then that gives us to 5.3 some properties that I'm going to talk about it. Okay, so it's almost 8:30. Come back in 10 minutes, and we try to give you one more section of the properties. Okay, this part was the part that you mostly use in calculus, and those properties are easy. You may have seen it before, but we are going to cover it. Okay, in 10 minutes, and then we continue. Okay, let's get the more property of the ln function. Okay, or the log function. These are from section 5.3. It's all algebra. You get a couple of questions from this one on your next test and quiz, and it's going to be easy question. Okay, so this is 5.3. Okay, 5.3, some algebraic property of the ln function. Okay, properties or more properties of the logarithm. Or the logarithm functions. Okay, that's it. So we are going to list those properties that we talk about it. Okay, so the I just recall that formula again because I want to refer to it. Okay, so again we recall that we say y is equal to the log of x with base b if and only if x is equal to the e to the y. So anything you want to talk about it, you are going to use these properties. Okay, so the first one we already talked about it, so I'm going to rewrite it again. Okay, we talk about the domain, positive numbers because of the excess, and the range, all real numbers. Range, all real numbers, or negative infinity and positive infinity. Okay, now the other easy property that we're going to be interested in, and we use it. You see, this is going to be useful. If you want to find the log of b with the base b, look at this one. If you replace the x by b, so here is going to be b. Okay, this is, I'm sorry, this is, I made a mistake here. I just used the log, so this is b to the y. If I use the ln, that would be, okay, b to the y. Okay, x is equal to the base is b to the y. Okay, now we go back. If you replace x by b, okay, that's it. B to the what is equal to the b to the 1. Okay, so this is going to be very useful. So the log of any number, it's on log of 2 and 2 is 1, 5 and 5 is 1. Okay, this is going to be the case. It's going to be, I'll just emphasize that. So this means if you get ln of 1, okay, sorry, ln of e, because the base is e, so ln of e is equal to 1. And if you go with the natural log, we go with the common log, log of 10 is equal to 1. Okay, so if the number match the base, the result is 1. In case of the ln, the base is e, so e would be 1, 10 would be 1. And if you have any doubt about it, you can use your calculator to check it. Okay, so this is going to be one case. The other one that we're going to use, this would be again useful to know. If you want to find the log of 1 at base b, again, you can use your calculator to see it, or look at this one. If you replace x by 1, if you replace x by 1 over here, so you want to know b to what is equal to 1. B to which power is equal to 1. You know that b to the 0 is equal to the 1. So log of 1 is equal to the 0. Very useful. Okay. Ln of 1 is equal to the 0. And the log of 1 is equal to the 0. Okay. So these are some easy points, but so useful. So useful to get. Anything else, use your calculator. If you want to find the log of 2, ln of 2, ln of 3, we're just using calculator. But these are the one that we call them, okay, exact number, exact value. Okay, so that's a 1, 2, 3. What's going to be the fourth one? Fourth one is very famous property of the log, and this is it. If you have the log of x to any power, x to the n, at any base, we can shrink it. Okay, we shrink it, or we just bring the power down. Okay, so this is going to be equal to n log of x at base b. It's used in calculus and this course. Okay, when the number is very big, okay, we take the ln to make it shrink it. You see, when there is an earthquake, they say, you know, the intensity of the earthquake is 6.5, 6.2. It's not 6.2, 6.5. The number is big, but they use the log or the ln of that number. That's why you get, you know, you get some easy, you shrink it if you like. Okay, so this would refer to it as a power rule. Okay, power rule. So any power, you bring it down. Okay, that's one case. These are the one that's going to be used. We give you two problems, and two problems are going to be this. Okay, so that is the fourth one. The fifth one. The fifth one, we called it a product rule. If you have the log of the product, x1 times x2 at the base b, any log, ln, anything. So it's going to be equal to the log of x1 at base b plus log of x2 at base b. So if you have any product, you can break it into parts. We break it into parts, it's going to be log of x1 plus log of x2. This would refer to it as a product rule. So product rule. Okay, the power rule, product rule. So again, this is the one we are going to use. Now, what's going to be the next one? The next one is if you have a quotient. If you have the log of a quotient, if you have a log of x1 over x2 with the base b, we can distribute it as a difference. It's going to be log of x1 at base b minus log of x2 at base b. So if you have any product, you can rewrite it as a sum of two log. If you have any quotient, if you get any quotient, you can write it down as a difference of two log. This is going to be called quotient rule. Okay, so that's a quotient rule. Okay, so the product rule, you bring the power down. Sorry, the power rule, you bring the power down. The product rule, you change into the product into the sum. The quotient rule, you change any quotient into a difference of two log. Okay, difference of two log. So that's going to be number 6. Okay, and the last one is why we like ln function rather than any other, and why we use it in calculus. Why? Because you can change it. You see, if you have a log of x with the base b, you can rewrite it down as it's going to be equal to the ln. Okay, it's going to be ln of ln of x divided by ln of b. You see, ln of b is a number. It's ln of 2, ln of 3, ln of 5. You can use your calculus and you'll find it. So this means ln of x is almost like the log of x. So that's why in calculus they work with ln x, because it's easy. And if you give me anything other than, you say, oh, change it. Okay, change it. They call it the change of base formula, if you like. Okay, so that's the reason that we just focus on the ln rather than any other type of the log function. Okay, so there you are. all the possible properties of the log function and 3 problems. Okay, are you ready? Just give you all those 3 and you get quite a lot in your book. Okay, let's check those 5s, pick 5 nice one, and you will see the one that we are interested in your next practice quiz. Okay, so the problems. The first one, example. In the first one, they are going to ask you this expression. They ask you to, okay, we want you to evaluate, okay, evaluate the exact, okay, evaluate the exact, or find the exact value, find the exact value, if you like, of each quantity, of each quantity. You see, the exact mean, don't use your calculator, okay? Do not use any calculator. So exact means, you see, you are going to use only this one. Look at this one. Log of b at b is 1. ln of e is 1. Log of 10 is 1. Okay, nothing else. Nothing else means you can use these properties if you like. But when they say exact, don't use calculator. Okay, if there is going to be ln2, you have to use your calculator. So knowing only this fact, the fact that the log of any number with its own base is equal to 1. Okay, so that's we call it the first question. You get quite a lot in your book. Let's see how we're going to do it. Number 1. Number 1, they ask you to find the log of 32 with the base 2. There are different ways to do it, but this is the way I suggest. You see, you want to use only this fact. So the base is 2. So you have to write it down as a log 2, 2. So what you do is you try to write the 32 in terms of the power of the 2. Okay, you know that 32 powers of the 2. So that give a log of 32 at base 2. You rewrite the 32 as 2 to the 5th. 2 to the 5th power rule. We can bring the power down. So it's going to be 5 times log of 2 at 2. It's going to be 5 times 1 is equal to 5. Okay, that's the meaning of the precise. Okay, no calculator. Okay, just using the fact that the log of 2 at 2 is equal to the 1, and we get it right away. Okay, that's the type 1. Any question? That give you a good experience on how to change it. Different way to do it, but this is the easiest one, or this is what they mean. Let's see what's going to be the next one. Give you various types so we get the experience, and then you'll be ready for the, if it's going to be complicated. Okay, let's see. What is going to be the log of 0.001? That's the one. What's the base of this log?
Is that 0.001?
Yeah, 0.001.
Okay.
What's the base of this log? Okay.
1.
No.
0.
No, Chris is
There
right.
is no base.
No, there is a base, 10.
Oh.
Remember, when there is nothing, the base is 10. It's a common log. Okay, the base is 10. So since the base is 10, you have to write these numbers in the terms of the powers of the 10. Because you have only, okay, you have only that, the fact that, okay, it's going to be 10, 10. Okay, So yes, the base is going to be 10, okay, because it's a log. So just think about it. Since the base is 10, you know that the log of 10 is 1, okay? So if you can change it, then you'll be able to do it. Any suggestion in terms of the powers of the 10? So let's write it down again. You see, what is this number? This number is what? Is 1 over 1,000. 1,000. Okay, now you know that the 1,000 is 10 cubed. And you bring it up, 10 to the negative 3. You see, it's going to be log of 1 over 10 to the third. You bring it up, that gives you log of 10 to the negative 3. Okay, so you see the base would guide you through. So this is going to be, that's it. This is, I just repeated, log of 10 to the negative 3, bring the power down, negative 3 log of 10, but log of 10 is 1. So that gives you negative 3. Okay, so without any calculator, log of 0.001 is equal to negative 3. Okay, just look at the base. The base is 10 now. So you have to use the fact that the log 10 at 10 is always 1. Okay, any question? So another type. And you have it in your book again. Let's see, next one. Next one, something with the ln. Remember, for the ln, the base is e. The base is e, so ln of e is equal to 1. So suppose you want to find the ln of cube root of e. Okay, cube root of e. Any suggestion? You get this one?
Can you make the cube root e to the 1/3 and then
That's
move
it.
that to the front of ln?
Yes, that's it. Very good. So it's going to be ln of the cube root of e, yes. We write it down as ln of e to the 1/3. Now we bring the 1/3 down, and ln of e is 1. Okay, very good. 1/3 times 1, which is a third. Okay, so the ln of cube root of e is equal to the 1/3. Again, no calculator. We're just using the fact that the e is, that the ln, the base is e. So the ln of e is log of e at e, or with e. So that gives 1/3. Okay, any question? So this is another one. Now, how about the next one? The next one is the log of negative 64. Okay, negative 64 at base 8, or with base 8. The base is 8. Any suggestion for this one? Number. You see, it's a negative number. Remember, you cannot find the log of a negative number, because the domain of the log is positive numbers only. They give you 64, it's misleading. 64 is 8 squared. Okay, but this number is negative. The log of a negative number is not a real number. We talk about it's complex numbers, but you can say does not exist, so it's undefined. Okay, if you want to show off your knowledge, you can say that it's not a real number. Okay, so just one of them to answer it. Okay, you can say that it does not exist. It's undefined. Okay, this is it. It's undefined. Undefined because inside must be positive all the time. Okay, inside must be positive, and you cannot have a negative number. So be careful. In the meantime, they may give you something, so then you are ready for it. Okay, any question? So just give you various property of this one that you see it in your assignment. And there is one more. Let's see how we're going to take care of this one. You see, you have something like this is it. Yep, and in your book, this is going to be, how about log of, this is, I just want to give you just the precise one, is log of 72. Okay, it's going to be log of 72 at base 6. It's one of the problem in that book, you know. And then this is going to be log of 2 at the base 6, with the base 6. You see, that should give you an idea, because log of 2 with the base 6, you cannot do anything about it. And you don't want to use your calculator. So what you should try to do is you have to try to change this one into a single log to be able to take care of both of them. To change it to the single log, it's a difference. Remember, we can change the difference into a quotient. The quotient rule, okay? So the solution is going to be, so the log of 72 at 6 minus the log of 2 at 6. We can rewrite it as a log. You get the quotient. Okay, on the top we put the 72, down the bottom the 2, but the base is 6. Okay, but 72 over 2 would be 36. So that will be log of 36 at 6. But the 36 is 6 squared. So that gives you 6 squared at 6. You bring the 2 down, and then the rest. Log of 6 at 6 is 1. So that gives you 2 times 1, which is equal to 2. Okay? You have 1 in, maybe that's the same one, I don't remember, in your book. So that gives you some idea of, you know, the things that you can do with these properties that we have. Okay, and if they ask for the exact value, this is what you can do. Otherwise, you know, you can use your calculator. Okay, any question? So that's the first problem, just exact numbers. Ready for the second one? Now, this second one is quite interesting, and you use calculus. This is the only one that you are going to use in calculus. What is going to be this one? You see, when you are going to be in application mode, you may have some very complicated, you know, expression containing the ln or the log. So what you can do is you can break it into parts if you like. Something complicated, you make it as easy as possible. Now, how are you going to break a log into parts? You are going to use those 3 properties that we talk about it. A power rule. If there is any power, we bring it up in front. If there is going to be a product, we write it as a sum of 2 log. If there is going to be any quotient, we write it down as a difference. So these 3 quantities are the one that we're going to use for these type of problems. Okay, so we give a 1 and a couple of them, and this is the most popular example, if you like, of this section. So this is how I'm going to ask you. It asks you to expand it, if you like. That's it. That's the one. So we ask to expand each expression. In your book, they explain it. They say expand this each expression so that in your final answer, you are not going to have any power, any product, or any quotient, but you know it yourself. So the expansion means break it into parts. Okay, so let me just give examples, then we explain this. So we start with this one. You get something like ln of x squared y to the 5th. You see, we can expand it if you have, a log of a product or you have a log of a quotient. Because the product would be changed into the sum of two log, the quotient can be changed into the difference of two log. This time you have the product, so we just use the product rule. You see, that's it. The main operation is multiplication. So we say the ln of x squared y to the fifth is equal to the ln of the first one plus ln of a second one. That's the ln of a second one. Okay, it's a product, we change it to the sum. Now we can continue because we have powers. So put the powers up in front. So that gives you 2 ln of x plus 5 ln of y, and then you're done. You see in your final answer, there is no more power, there is no product, and there is no quotient. So you did the expansion. And the application is, if you know what is ln x, and you know what is ln y. Suppose ln x is 5, ln y is 10. If you substitute, that gives ln of x squared y to the fifth. This is the way, they use it in algebra, if you like. But the idea is for future. You see, change it to the something easy. Okay, that's the type 1. Any question? I have another one, then I give you the one that we use in application problems. So what's going to be the next one? The next one, something with the quotient. You see, log of, just using different types of the log. You may be given something like, let's say this is going to be what? This is going to be y squared, or y to the third, over z to the fifth. Again, you want to expand it, we have a log of a quotient. If we get a quotient, we change it to the difference. Okay, so the solution is going to be, that's it, log of y cubed over z to the fifth is going to be the log of the top one minus log of the bottom one. See? Quotient into difference, product into the sum. But you're not done. You can bring this power down. So 3 log of y minus 5 log of z. You see? Nicely done. Okay, that's going to be the second case. Any question? This third one, I just used it yesterday for calculus. Suppose you have ln of cube root of x to the fifth minus 1. You want to simplify it. Okay, again, we don't like the radicals, even in calculus. So you change the radical first. So the solution is going to be, it's ln of cube root of x to the fifth minus 1. You rewrite it, you know that. It's going to be what? Ln of x to the fifth minus 1, everything to a third. But it's the power, you bring it down. 1/3. Ln of x to the fifth minus 1. In calculus, we have one operation, we call it differentiation. And we apply to this function. If you want to apply to this one, it's complicated. But this is so easy. So automatically you do it yourself. You're not going to be asked, to use, to rewrite it, use property of the ln. No, you must know it in advance to be able to do it. Okay, any question? So the actual one for calculus is this one. Let's say I'm going to simplify it. Are you ready? Suppose you have the log, then you have, okay, this is it. You have the fifth root inside. Inside you have 2x plus 1, and this is going to be x squared plus 3. You see, seems to be very complicated, but it's not. Okay, we want to simplify it or just expand it. The way we do it, we have to take care of the radical first. Okay, we write it down everything to a fifth. Then we can bring the fifth down. When you do the radical, then there is a quotient. Then you can continue. Okay, so this is going to be the solution. The solution is going to be equal to, we take care of the radical first. So it's a 2x plus 1, x squared plus 3, everything to the parentheses, everything to a fifth. Okay, now we can bring the fifth down. Fifth log of, okay, 2x plus 1, and this is going to be x squared plus 3. You see, but you're not done because you have a log of a quotient. Log of a quotient, you change it into the difference. So it's going to be a fifth. You need to open up a parenthesis. It's going to be log of the top. Log of the top, 2x plus 1, minus log of the bottom, x squared plus 3. You see, now you're done. And this is so easy to work with, rather than that complicated one. Okay, any question?
Would you get marked off for distributing that 1/5 to both
Well, that's
sides of the
better.
log?
If you do it, it's better.
Oh, okay.
It's better. You just be good. You don't have to, but if you do it, that's better. That's going to be the one, because the aim is you don't have anything related to the log. Okay, if you do it here, you say, oh, you have a log of quotient. Why didn't you do it? Okay, that's fine. So this is going to be the expansion. So popular. This is one of those only property that you need really for application in future. Now the last problem, let's give you one more till we finish it. The last problem is the other way around. What does it mean? This means, you see, this would be given to you. You're using two log. They ask you to put them together so that you have only a single log. Why we need it? If you want to solve so-called equations containing the log, we need this type of ideas, because we have to isolate the log. We can isolate it if it is only a single one. Okay, and it's very easy to do. Look at this, the one that we did is playing back. You see, you want to change this one to the single log. Step 1, move the numbers up. Step 2, any sum, change it to the single log with the product. Any difference, change it to the single log with the quotient. Done. And it's only just, 2 cases, nothing else. Okay, so this is, we put them together, we condense it. That's the expression of your book. They ask you to condense the expressions, okay? So this is just used in algebra. You're not going to use it in calculus in future. Okay, so the last example is going to be, we want you to, combine them, write it. The expression I use is write each expressions. Okay, this is going to be the case. Okay, you say write each expression using or as a single logarithm. Okay, that's the idea. It's only 2 cases. This is nothing else. Okay, the best they can do is this one. They may ask you 2 ln x, okay, plus 7 ln y. So step 1, move the coefficient up. Step 2, any sum of two log is going to be a single log with the product. Any difference would be a single log with the quotient, and then you're done. It's not a big deal, and there are only very limited cases. So 2 ln x plus 7 ln y is equal to, so we move the numbers up, it's going to be ln of x squared plus ln of y to the 7. You see? Now you're going to get the single log, single ln. Since it's a plus, it's just a product. X squared, y to the 7. If there was a negative here, difference, you change it to the single log with the quotient only. Okay, it's not a big deal. Give you another one to finish it. Any question? So we are interested in this one, but we give you one of these, okay, on the test. So let's give you something with the difference. You see this one? You may be given 3 log of x, 3 log of x minus 1/2 log of, we give 1/2 log of x cubed plus 5. You see? You want to switch it into a single log. So you have to move these numbers up first. So the solution is going to be, so it's going to be equal to the log of x cubed. Okay, move the half up, minus the log of x cubed plus 5 to the 1/2. Now we change it to the single log, but you have minus. With the minus, you need the quotient. The top x cubed, the bottom one, x cubed plus 5 to the half. Okay, but you know this, you have to change it to the radical. So it's going to be log of x cubed, a square root of x cubed plus 5. That would be the final answer. You know, as you did it, you know, the other way around. And there was a radical, you change it to the rational power. So if there is a rational power, you change it to, so it's not a big deal. This is easy. Just 2 cases, a difference, let's move the numbers up. If it's a difference, you get the log by the quotient. If it's going to be the sum, you get the log as a product. We use it for the solving the equation. Okay, next time. That's it. That's section 5.3. Try to look at the problems. Okay, pick some nice one. There are quite a lot, something like 100 problems in this section, but you don't need all of them really. Just check the one that I did for the application, and those, you know, I try to post the next practice quiz in advance so that you can have a look to see what is going to be on. Okay, that's it. Any question? So you just check your, you know, your test when it's done. I send you a message, and then anything, then let me know. Then I correct it for you. Okay, take care and see you on Monday. Have a good night. Bye-bye.
Thank you. Bye.
Bye-bye. Have a good one. Take care.